We used to have 5 offices dispersed throughout the suburb areas, so we're part of the solution for urban sprawl. We're coming back downtown. So my talk today is going to be focused on change detection, primarily using satellite-derived data, and talking about at least half a dozen or so different projects. Briefly, can't give a lot of details on those because they are to private clients. But 3 areas of particular concern are water quality, wetland hydrology, and ground subsidence. So water quality. So there are a variety of variables that can be derived using satellite data. Those being turbidity, algae, chlorophyll A, dissolved organic matter, aquatic macrophytes, and thermal plumes. We have now a very nice history of satellite data going back now 40 years, thanks mainly to the Landsat series of satellites. Do a lot of work with DFO, identifying fish habitat and rehabilitation of fish habitat. We've looked at things like water velocity and shoreline erosion, especially erosion of peatlands and how that affects mercury levels in fish. So here's an example of some of the work we've been doing. This is with a First Nation community. This is a Landsat 8 image taken last fall. We did a quick and dirty K-means classification. We're hoping to get some data from Manitoba Hydro so we can calibrate and validate some of these unique signatures that are being picked out from the imagery. The big concern here was a 2-mile channel that was under construction in 1974, and how that has actually changed the sedimentation process and shoreline erosion within the northern lake there. That's Play Green Lake. So when I first got onto this project, the first thing I did was like, oh my God, I hope we have a nice cloud-free Landsat 1 image prior to the breakthrough of 2-mile channel, which is located right there. And luckily enough, we did have 1 image. So now what we have done from a change detection standpoint, again, looking at our September 22nd, 2004 image, you can see how, and you can see now 2-mile channels now punched through. You can see how that affected the course of the water when that channel was ultimately constructed. And the main purpose of that construction was to get more water flow into Play Green Lake. So here's a side-by-side comparison, false color composite of Landsat data. The 1974 data is a bit coarser resolution. It's 60 meters, whereas the 2014 data has been pan-sharpened to 15 meters. So I did a quick classification of land, created a land mask for 2014, draped it over our 1974 image, and now you can start to see where there's been some shoreline erosion. So if we zoom up on one of the points, you can see, even though the data is coarse, you can see in some areas there's been over 100 meters of erosion, and on some of the islands there's been upwards of 60 meters of erosion. So this was a project we did for the city of Calgary. This is in relation to the 2013 floods that occurred in Calgary, wiped out a lot of communities within that particular watershed, which was the Elbow River watershed. So we had a nice historical data set provided by NOAA of snow water equivalent data. This is all freely available on the NOAA website. So what we were looking for was average snow water equivalency within that particular watershed. The data is provided at 1 kilometer resolution, so you can get a very nice historical trend. This data is now being used to in the construction of I don't want to say a floodway, but it's a temporary reserve for snowmelt water to come into. They can basically create this reserve, and then as the water passes, they can now put that water back into the natural watercourse. So it's to help divert that snowmelt water that's coming down from the Rocky Mountains. So this is a little, not quite water quality, but same idea, using that same data set from NOAA. We were looking at snow cover data. This was a project we were doing with TransCanada Energy. They were concerned about wolverine denning populations or sites. So they were looking for snow covered days from 2009 to 2015 from a very specific time period from April 24th to May 15th. Can't tell you exactly why those dates. I assume it has something to do with reproducing for wolverines populations. So they wanted to know exactly how many days occurred between those dates, and then, which dates which areas were actually covered in successive years. So they needed anything over 4 to 7 years within that 7-year period. So again, able to use that very nice historical data set that's now at our fingertips. I'm going to talk now a little bit about wetland substrate hydrology. So this is a project we're working on with Suncor. I think they're the largest oil and gas company in Canada, so this is up in the Alberta oil sands. So the McClellan Lake wetland complex is actually surrounded now by major industry, and it's putting a lot of stress on that wetland. So Suncor wants to know how they're affecting the hydrology of this wetland, and in fact, is this wetland going to be sustainable? So we're using satellite data to actually take a look at this wetland. So we've acquired rapid eye imagery. It's 5-meter resolution, RGB, near infrared, red edge, a very good optical data set. And we've also acquired Pulsar 2 data. This is a synthetic aperture radar. It's an active radar. It uses an L-band frequency, so it has a very long wavelength, 23 centimeters. So it can actually penetrate the surface of a wetland. It can penetrate down to about 2 to 4 meters in many instances for bogs, fens, swamps, marshes, and things like that. So we've actually now segmented much of that wetland into different areas based on spectral signature, hydrology, and things of that nature. So the plan is to actually use our Pulsar 2 data to see if we can actually see hydrology being changed by this industrial pressure. So here's just a false color composite using the rapid eye data, and on the far right there you see the actual Pulsar 2 data, and I can actually sense whether the water within that wetland is stagnant or if it's moving. So the white areas represent the stationary data, while the black is the dynamic water or the moving water. So we did a very quick study, acquired an image on August 6, 2014, and August 30th of the same month, and we can see that there has been something going on here. Could be a rainfall event, we don't know, different recharge rates. But we plan to look at this, the hydrology of this wetland, not so much on a weekly or a monthly scale. They want to know what's going on like a 10-year or 20-year time scale. So we can do change detection not only on a yearly basis, but even on a weekly or bi-weekly basis. So now talking about ground subsidence. So the data that we're using for this particular work is synthetic aperture radar. These satellites will actually send electromagnetic pulses at the Earth, and actually receive that energy back. So they're not like optical satellites where they just are collecting energy reflected from the sun. They're actually sending their own pulse beams. The fully polarimetric SARs, they actually will record the phase of those EM waves coming back. So the wave is sent, it interacts with something, and it comes back. And the phase of that EM wave is now recorded. So these are interferomic SARs. So basically what's happening is the transmitted wave is being sent to the Earth's surface. The blue wave is being sent back after interaction with that surface type. We can create interferograms, which are basically just maps of phase, which angle of that particular EM wave is coming back, so we can record that information. Then what we do is we do a change detection of 2 interferograms, and we could do what's called a differential INSAR. So the path of the satellite remains constant, the speed of the wave remains constant, so the only thing that changes is the distance between that satellite and the ground, and that's how we can get ground displacement values. So again, this can be done daily, weekly, monthly, or even on a yearly time scale. So when we compare the 2 interferograms, we can get highly precise measurements. Typically, the smaller your wavelength, the more precise a measurement you can get. So you could do this with Pulsar 2 data, which is L-band. Of course, you could do it with RadarSat data, which is C-band. That's about 5 centimeters. But the industry standard for DNSAR work is TerraSAR X, and that wavelength is only 3 centimeters. So using that example, you can get accuracies down to 15 millimeters in ideal conditions. So some of the work we did out near Arizona, there was a major dewatering process going on, and the ground was actually sinking in certain areas. So we went in there with our interferomic SAR software and data, and we were able to determine which areas were being affected. And you can actually see here some of the scales. So we're talking, minute differences, plus or minus 30 millimeters. This is a project that was done for the city of Las Vegas. Of course, there's major dewatering in that area too. And we can see there the time scale. So this is in millimeters per year. You can actually see how the land surface of Las Vegas is changing slightly. And this technology is really good with man-made structures. So this particular project, this was done based on corner reflectance of buildings in Venice, Italy, which, as you know, is under a lot of deformation right now. So that was using corner reflector technology for the island of Venice. I think that's all I had to share with you today.